Yes, sir. We are live on YouTube as well as on Zoom. We can start the session, sir.
Okay. Can I get the link for YouTube Live?
Yeah, I will post it in the chat. Meantime, you can stay in the Zoom itself, sir. In case if there
Okay.
are any questions, I will post it here, sir.
Okay, you will post
Convenient
them.
for you,
Fine.
sir. Right,
Fine.
sir. Yes, sir.
Thanks, Murli. So we can start the session. Pranay, if you have any questions. Yeah, I know that you wrote something in the Google sheet yesterday, but perhaps you can ask them and we can have it in the form of conversation rather than a monologue.
Okay, first, can you tell me something about the Lavoisier theory?
Uh, yeah, Lavoisier theory is, I mean, do you mean essentially algebraic theory?
Yes, that.
Essentially algebraic theory, right? So how much of logic do you know? In order to understand this, you need to know something about logic. Do you understand like conjunctions, disjunctions there exist for all?
Yes.
Okay, so then
I know some propositional logic. Very
you
little
know
into
some
statistic.
proposition.
Yeah.
Okay, so let us consider like, the theory of groups, for example. Okay, how many axioms are there for the theory of groups?
So there is one identity.
Right, identity.
In the inverses, unique inverses,
Inverses
and
and
as associative law and
associative law. Fine. Just
right.
hold on a moment now. So once you know, let's talk about the law of associativity. Yeah. Then how can you write it? Law of associativity. It says that for all ABC, A dot B dot C is equal to A dot B dot C. Let's say dot is the multiplication.
Yes.
So this particular statement has a like this particular sentence. This is called a sentence. Yeah, this sentence has a specific type of structure. It says that this thing, like after this for all, like you can pull out all the for alls in the beginning, and after that, whatever you are writing, that is just an identity. Okay, identity in the sense that one, it's a quantifier free formula. Yeah, it's something equal to something else. Some kind of relation. The equality is the relation applied on two different things. So this quantity is equal to this quantity. So this is called, I mean, this is a quantifier free formula, simple thing. And it's a very simple type of quantifier free formula, like just it's an atomic formula, basically. Okay, so something equal to something. Now, such kinds of statements you can take, like for all is in the beginning, and then you are also doing it here. Inside there are atomic formulas. So this is called an algebraic theory. Yeah, in simple words. Okay, so this is the simplest form, and then essentially algebraic theory, it tries to relax some conditions on this. So basically, do you also know the definition? Like you can check that all the axioms for a group, they are of this form.
Yes.
Yeah. So similarly, now think about the axioms for a partially ordered set.
There is a quantifier and for all statement, right?
Yeah, I mean, don't say just a quantifier. It has to be a universal quantifier at the beginning.
Okay.
And then something in between. Now, actually, in categorical logic, there is a different way of writing this. So the for alls, the universal for alls, they can be written slightly differently. You can write a true. So there is a symbol for true. So true entails as in the turnstile symbol. The turnstile is written just like this. Yeah, the vertical line and an horizontal line. So true turnstile over ABC. Yeah, that this is a subscript. These are the variables which you are allowed to use. And then there is some there is an identity, there is an atomic formula on the other hand. So this is what we mean by a Horn sequent. Yeah, this is true,
Sorry, I
and then
didn't.
entails something else. Horn, Horn.
Oh, okay, okay.
Yeah, this is not a small H, it's a capital H because it's named after a person. Yeah, so capital H and then small ORN, it's name of a person, the Horn sequent. This particular thing is called a sequent. Now, categorical language, because it tries to analyze different fragments of first order logic. We are not talking about propositional, but rather first order logic here. So it tries to distinguish between different levels. So the simplest possible logic is that, let's say, this Horn logic. Horn logic is true, and then true entails something. And this right-hand side is always, right-hand side of that sequence is always an identity or an atomic formula. So that's the basic statement. And then you can try to make it slightly more complicated. So for example, I was asking you, can you tell me the definition of a partially ordered set?
Yes, it's a non-empty set with a partial order, and
Yes, so define partial order.
so so it's reflexive, antisymmetric, and transitive.
Right. So reflexivity, as you can notice, it just says that true entails Rxx, where the variable is x. So it is again a Horn sequent.
Right.
Yeah. Then the second one is transitivity. How do you write transitivity? That if Rxy and Ryz, then Rxz. So this one also you allow. Yeah, you take all these things, then that becomes an essentially algebraic theory. So to the left-hand side of the sequent notation, you have got a conjunction of two atomic formulas, namely Rxy and Ryz. So that is a conjunction of two atomic formulas. And then on the right-hand side, you have a single atomic formula. The true formula that we had earlier in the case of reflexivity or groups. Yeah, the true is basically the empty conjunction. So on the left-hand side of the sequent, you can have different types of conjunction, like finite conjunctions of atomic formulas. And on the right-hand side, you have a single conjunction. So this is what we mean by essentially Horn sequent and then essentially algebraic theory or a Laverre theory. When you can axiomatize a theory using sequence only of this particular form, then you call this an essentially algebraic theory. There might be some variations in the literature, but this lies at the heart of it. It is a syntactic condition. It depends on what quantifiers or connectives you can use. Pranay,
Does every algebraic theory came into picture like this?
which theory?
I mean, theory of groups. You said there are partially ordered two sets, and I hope rings are also formed
Yeah,
like
yeah.
this.
All the algebraic theories, not the theory of integral domains, though. Yeah, integral domains need to have a specific form, integral domains or fields, because it talks about some conditionals. And those conditionals have to, so for example, integral domains, yeah, perhaps we can do that. A is equal to 0 or, AB is equal to 0 entails A is equal to 0 or B equal to 0. Yeah, so that disjunction on the right-hand side, that is not allowed in an essentially algebraic theory. Moreover, if you are talking about the theory of fields, then in fields, you first need to say that 0 is not equal to 1. So negation 0 equal to 1, this cannot be fit into this format. And moreover, if the element is non-zero, then there exists inverse, two-sided inverse for it. Again, this cannot be expressed in this weak language. The language of essentially algebraic theories is very weak. You can't really say too many things, but most algebraic structures, like algebraic in the sense of universally algebraic structures, they can be fit into this format.
Okay.
Yeah, just okay. You're satisfied with the answer?
Yeah, I have to read the material also.
Yes, you should read something. Yeah. Yeah, the kind of literature that I was talking about, this is actually from Johnston's topos theory. Yeah, section D. So elephant, sketches of an elephant. Yeah,
Okay.
that is a
So
good resource for categorical logic.
I have his stone spaces, and it's my go-to book. I read it every day.
Not just
His
stone spaces. Look at the section D of
okay.
this essentially. I mean, categorical logic from sketches of an elephant. Yeah, that should be the go-to book. Stone spaces is very old.
Okay. So actually, I am reading now the locale theory, frames and
Uh-huh.
locales. So
Yeah.
so I had to read the stone spaces first.
But whatever material, like as far as I know, whatever material was covered in stone spaces, that is also present in this new format.
Oh, okay. I will look into it.
Yeah. And
So,
one more feature I should talk about, like for essentially algebraic theories, is that the categories of models of essentially algebraic theories, they are LFP categories, if I'm not mistaken. Locally finitely presentable. They have all the nice properties that you desire. Because these are Cartesian theories, so therefore you will get this.
okay, suppose you want a good category. Okay. So, what are
Uh-huh.
the properties you want there?
I mean, what is the meaning of a good category? Now you have to specify it.
So in case of locale theory, they need Cartesian closed, um,
Right,
presence of small limits and all. So
right.
in that case, they say the category is good.
Yeah, I mean, the definition of good depends on your context. Yeah, we can never define abstractly what is a good category and what is a bad category.
Okay.
Yeah, so there is a YouTube query by Virat. So Lave's fixed point theorem, I'm not aware of. Yeah, specifically that thing, I'm not sure I know. Deepankar, do you know anything about Lave's fixed point theorem? Okay, perhaps he's not here. Uh, yes, maybe I should go back to the form. I think it was only the two of you asking questions. So, well, Stone and Priestley dualities, you have asked about it. So you can obviously get, once you understand the concept of duality, Stone and Priestley type dualities, they are special cases of them. Stone type duality has to do with propositional logic, classical propositional logic, and then Priestley type dualities, they talk about various subclasses of the class of distributive lattices. So it's algebra and topology kind of balance. On one side, you have stone spaces, totally disconnected, Hausdorff compact spaces, and on the other hand, you have what Boolean algebras. Yeah, Boolean algebras are the algebraic embodiments of classical propositional logic. So Boolean algebras form the syntax part, and the other side, it forms the semantics. Yeah, because the elements of this so-called stone space, they are valuations on this. So and then you topologize those things. So similar thing you can do with I mean, if you have less restrictions on this side, then you will have more structure on this side. It's always about balance. Yeah, syntax semantics dualities. It's a special case of that, syntax semantics dualities, stone duality. And if you add more conditions on this side, then you relax some conditions on this side, or vice versa. So you try to relax this side, yeah, that distributive lattice you are trying to relax to, I mean, Boolean algebra to distributive lattices, that is a relaxation. So on this side, you will get more properties. And well, I can also give you some other reference, as in 2 years ago in 2022. And we organized a school. It's called Indian School on Logic and Applications, and it was held here at IIT Kanpur. And over there, I talked about categorical logic. Those lectures are available online. And stone duality was covered, and there were other people talking about Priestley duality over there. Yeah, Marcus Tressel and Nick Bezanishvili, they spoke about these other things as well. So you will find more material available online. Like basically all these algebraic and topological dualities was the purpose of organizing that school. Hope you heard me.
Yes. So what is the main reference for syntax semantics duality?
I think there should be a book by Davy and Priestley. Yeah, Brian Davy and Hilary Priestley. They have written a nice book. And
lattices and order.
oh, I don't remember the title of the book, but I met Brian Davy, and yeah, he has a book with Priestley's. There should be only one book. So that should be your go-to book for dualities.
Okay.
And yeah, you might be interested in these lectures as well. Yeah, they will give you more references because I don't remember exactly right now. And yes, IIT algebras, I think your question was, yeah, what is the motivation behind IIT algebras? I hope you know what it is. We are just trying to relax the implication or negation and intuitionistic, the internal logic of intuitionistic logic, what should I say? The syntactic embodiment of intuitionistic logic is IIT algebra. So just like classical algebra gives you propositional logic, classical propositional logic gives you Boolean algebras. So intuitionistic logic gives you IIT algebras. And just to say something more about this, basically you take logical equivalence classes of formulas in for a propositional language. They form a Boolean algebra. So similarly, if you take intuitionistic logic as your base and you take logical equivalence classes of formulas, then you will get an IIT algebra. So that's the answer to the first question. Then how is it connected with intuitionistic logic? Yeah, I already mentioned what it is. And why the IIT implication has a left adjoint? Because the IIT implication is defined to be the right adjoint of the meet operator. Yeah, it's not the other way around. Implication doesn't come first. Implication is a consequence. You are demanding that the meet with a specific element has a right adjoint. Yeah, that's the important point here. And there is another question by Viraj. So insights on infinity categories and their abundant applications as a foundations to the areas like derived algebraic geometry and spectral algebraic geometry. I'm not an expert on this, so therefore I will request Deepankar because he knows more about this. So I will request him to talk about it.
Well, I mean, since this course was on ordinary category theory, I wouldn't speak much about infinity categorical language. But more or less, what you try to do in infinity category theory is to try to, correct some defects in ordinary category theory. So, for example, if you're doing homological algebra and naturally you are passing on to the derived category of, let's say, a given abelian category, then the problem is that you lose a lot of information once you localize that quasi-isomorphism. For example, if you have two chain complexes which are homotopy equivalent, you cannot really determine whether they were homotopy equivalent passing on to the derived category. So the idea of infinity categories is to capture this lost information. So in a derived category, you do have identification of quasi-isomorphisms, but in the infinity derived category, you put how they were quasi-isomorphic, this information, into higher cells. So, I mean, you know of the category of categories, which is ideally a two category, where you have morphisms between one morphisms. So naturally, you can think of a three category and therefore an n category, where you will have k morphism between every k minus one, two k minus one morphism. And an infinity category would, in this sense, be a category where you have morphisms between all dimensions of morphisms, right? So that is about infinity categories, but this is a very vague idea. You can write down a precise definition of an infinity category, but those are just models of infinity category, and there are several of them. For example, the Lurie's version of infinity categories are using simplicial sets. There are complete Siegel spaces. You can use simplicial categories enriched over groupoids, and so on and so forth. Okay. So the basic idea would be that these are categories enriched in a suitable way over infinity groupoids. You can choose any model of infinity groupoid and then define your, appropriate version of infinity categories. Now, coming to derived algebraic geometry and spectral algebraic geometry, I just say that they're not really uh, algebraic geometry as you think of it, but they're modifications of that. Um, and of course, why would one do that? Because there are issues associated to things, for example, say intersection number. They might not be well defined. I am not sure exactly, but because you have the definition involved higher torches, higher Tor functors. Therefore, if they do not vanish, the intersection number might not be well behaved. So there are certain issues associated to this, and the basic problem is that the structure sheaves associated to schemes are discrete objects, and some people try to fix this using infinity categories. And the basic observation that was made was that instead of starting with ordinary rings, you start with derived rings and do a similar version of algebraic geometry by patching up affine versions of those derived rings. And these derived rings are actually constructed in a way that instead of having set theory as a constructive block, you start with infinity categories, which are nice models of spaces which are not discrete. Say, for example, you can have the infinity category of topological spaces or simplicial sets. And you can, instead of starting with sets, you start with the category of spaces as your building block, and then you start doing algebraic geometry there. You can also have infinity rings. So these two, give you derived and spectral algebraic geometry. But yeah, let's not talk more about it. So, oh, there are YouTube queries. Prof. Lover is fixed point.
Yeah, YouTube query. The first one, thanks for the reference, Virat. I will have a look at it. Like I don't know about this, that there is something called Lavet's fixed point theorem. The other
the
query
one
also I
that
would,
so
yeah, you
sorry
should
to interrupt.
answer, Dipankar. The other
I mean,
one
Lavoir's
is,
fixed point theorem, I would say that I don't remember its logical connection, but it more or less says that, in a Cartesian closed category, if you have an epimorphism of some kind, so pointwise defined epimorphism. Okay, people call it maybe pointwise surjective map from A to some function complex, then every endomorphism of that object would have a fixed point, something like that. It has some connection to this Laveri theory, but I don't remember exactly.
I mean, not everything that Lavere did has to be connected with each other, I
No,
would
but I
say.
remember this theorem was this is also there in type theory, so it must be something logical,
Yeah.
but I don't remember. Yeah. More or less, this says exactly the following. I guess a to b to the power a. If this is a pointwise surjective map, then every endomorphism of b has a fixed point, something like that.
Mhm.
Okay. So
Also look
can you
at the other
generalize?
two. Yeah.
Can you generalize the notion of étale fundamental group on the smooth topology?
Smooth
I mean, smooth
topology.
topology is more broader in the context of stacks than the étale topology. Okay, so I would ask, who is asking this question?
Virat.
Where is he?
He's on YouTube. He's just watching on YouTube, not here, not on Zoom.
Okay, so first question would be, which definition of étale fundamental group are you taking? The classical definition does not bother about the topology, right? So it is so the classical étale fundamental group, which is just a group, a profinite group, is the automorphism group uh, of the functor uh, of see more generally. I can say that if you start with any Galva category, then the Galva group is going to be the automorphism group of the associated functor. Now, if you start with, let's say, finite étale morphisms on a scheme, the site of finite étale schemes over a scheme, base scheme is, let's say, then there is a functor for every geometric point x. You can construct a functor which is given by fibers of that geometric point, right? And this forms a Galva category. The endomorphism group of this functor is the étale fundamental group, right? Now, the whole point of why this construction works is that the category of finite étale, if you have finite étale morphisms, then the fibers are finite. And therefore, you can have a Galva theory there. Unless you have that the functor is exact in a nice way and has finite, uh, results, the theory would fall apart. So therefore, uh, only the finite étale morphisms would help you construct étale fundamental group in the classical sense, and it doesn't bother about the topology. So I don't know what you are exactly asking.
Maybe he can clarify.
Yeah, maybe you
If
can
he
clarify.
writes another
It,
message, then
this
we
does
will.
not have anything to do with the topology as such. It is a purely categorical construction, starting with the category of finite étale morphisms over a base scheme and the fiber functor of a geometric point. Okay. Well, there are now modern versions of defining fundamental group for toposes. So if you know how to do that, then you can immediately say that it doesn't matter how you define it, they're going to be derived in if you do it, of course, correctly. So, So yeah, Virat, please clarify if you're talking about this fundamental group or Nori's version of fundamental group, which is, quite complicated and I will go back.
And it would have been better. Yeah, I mean, even though there is an
He
option
could
of
join.
YouTube Live, yeah, exactly. So joining Zoom is far better than.
Yeah, he's right. It claims that broad generalization of Cantor's theorem. Yeah, it's a diagonal argument, so it's a generalization of Cantor's theorem, as I said. The statement was about making, okay, I'll not talk about it, but yeah, of course, this was a diagonal argument. So Cantor's theorem is the generalization of Cantor's theorem. Many other fundamental.
Yeah, I was talking about the category of schemes one. Yeah, that is what he's writing.
No, this one is about Lavery's fixed point theorem. The first one is about Lavery's fixed point theorem.
No, the latest message from him says that I was talking about the category of schemes one.
Yes,
So
of
this
course.
is, I think, related to et al.
Where does he write? Another. I don't see this. Can you post
that?
This
Is on YouTube. That is on YouTube
see.
live chat. Yeah.
Well, of course, of the category of schemes, but the way you define it has nothing to do with the topology. You start with a base scheme, then look at the category of finite étale morphisms over the base scheme, and then given a geometric point, construct the fiber functor to the category of sets and look at the automorphism group of that functor. And that is the étale fundamental group. Because you're starting with étale, the category of finite étale morphisms, it is called the étale fundamental group. So, unless you are talking about Nori's version of étale fundamental group scheme, which is a different. I hope that clarifies.
Okay.
Yeah, what else?
Yeah. Pranay, if you have any other questions, you can ask. And I can see that we are all going on tangents here in this discussion session. Nothing is really about the course.
There is nothing category theoretic.
Okay, I'll ask one category theory question. So what was the main reason of defining the enriched categories? I mean, the motivation
what was
behind
the main
it.
reason?
First
I mean, you are asking me what happened, what went on in those people's minds 50 years ago.
Yes.
When
you can recall it from monads if you want.
Okay, I don't know what was going on in their minds, but obviously, like if you think about abelian categories, then the home sets have got some extra structure. So I think that is what motivated people. The main purpose, I would say that set theory differs from category theory in the sense that the collection of all sets is not a set. So, however, this Russell's paradox can be avoided over here, like categories with functors, they themselves form some other category. Yeah, unless you are talking you are worried about size issues. So, in a similar spirit, you should never stop. That would be my guess. Yeah, even when we are talking about the home sets themselves should be coming from some other objects. Once you start looking at simple, like take the category of sets, and you start looking at the structure of the home sets and how functions interact with them, the pre-composition, post-composition, and those things. So it's automatically clear that the category of sets is actually working at the level of home sets as well. And perhaps just that observation led to the definition of enriched categories. That would be my guess. And now people are also talking about the generalized metric spaces, where the home sets themselves could just be elements in real numbers. So I think once you can push an idea further, then you can take it very far. As long as you see some kind of category theory present over there, then you try to exploit it, and that leads to this enriched version. And then you also sort of, I mean, there is a like, what are the properties of a given category? You can usually attribute them to the structural properties or the enrichment properties. You can distinguish between those two different types of properties. I think that's a beautiful piece of theory. For example, toposes and abelian categories. The toposes have this property that pullbacks of epimorphisms are again epimorphisms. And abelian categories also have the same property. But the reasons are entirely different. So then you can ask the question whether it comes from the enrichment, just because it, I mean, enrichment as in just because it happens in the category of sets and the category of abelian groups, the enriching categories, or does it happen because of some specific axiom or a collection of axioms which define the classes of toposes, or I mean Grothendieck toposes or Grothendieck abelian categories. You have to investigate these things. So some properties come from the enrichment, some properties come from the axioms with which you define that class of categories. You want to add something, Dipankar, to this enrichment?
Well, I mean, there's nothing to say more about this, but maybe if you look at this dilemma between why category theory and not set theory, and some stupid dialogue between those two. Now, some people would say that category theory is an alternate foundation, but then it heavily depends on the category of sets, right? So a natural question would be, can you really get rid of them and move to a world where I just feed in some basic theory to you, and then whatever you want to construct has to be based on that. Say, for example, when you're growing up, instead of teaching you elementary numbers and sequences and sets, I will just teach you a theory which does not care about all those things. Let's say right away, I will teach you the theory of groups without even teaching you sets. Then can you, so then you wouldn't even have a notion of a function between sets. You'll just have the notion of group homomorphism between groups. If I ask you to develop further machineries using that, then the natural idea of a category would be the category which would be enriched over groups, right? So apart from that, I don't see any further reason why historically they thought of this. But eventually it became obvious that if you want to simplify your theory and write down them compactly, then enriched categories is the best option. Right? So for example, as I was talking about infinity categories, it becomes heavily complicated to write down all compatible equations in all degrees together. So it is better to talk about a category which is enriched over infinity group points. And then you can write down a single or a few statements for the whole theory. That's all.
I mean, you are talking about a fundamental mathematical principle that if you have some, like if you get at least two examples which have something in common, then how do you identify the common part? Then in this case, it turns out to be the enrichment, the structure on the home sets. They behave nicely. And there is another question from Virat, like he's confused. Étale topology is actually a Grothendieck topology. I do agree with that. I think Dipankar was talking about something else.
he asked about ethyl fundamental group.
Fundamental group. Yes, exactly.
And
exactly.
the name ethyl being there does not say it is coming from the topology. It is the automorphism group of the functor, as I mentioned several times. So maybe you should read a little bit about it. Okay.
I think he is worried about like whether there are different topologies, Grothendieck topologies on.
Why don't you join this?
Yeah, I don't know
Ask
that.
him
That's
directly. Okay, maybe I'll still add this. So the idea came from topology, right? How you construct the fundamental group of a topological space was not applicable to the case of schemes, right? You cannot just bluntly define the fundamental group of a scheme to be the fundamental group of the underlying topological space, because that wouldn't care about algebraic difference, right?
okay, fine.
Okay. Yeah. So therefore, Grothendieck tried to, get an algebraic description of the of a fundamental group that would act nicely and would allow him to distinguish between schemes by computing the fundamental group. So what he did was he passed on to the theory of covering spaces of topological space. For a nice enough topological space, you can actually construct the fundamental group without using homotopical ideas, just using covering space ideas. If you given a topological space, if you look at the category of finite covering spaces, covering spaces, I hope you know, then
It's a different question. You just keep talking.
oh,
Yeah,
I see. That's distracting actually. Yeah. So what else is? Yeah. So if you are given a nice enough topological space and you look at the category of finite covering spaces, then you can actually get not exactly the fundamental group, but up to some correction, you can get a profinite completion of the fundamental group. That is precisely the endomorphism group of the fiber functor of the category of finite covering spaces of the given topological space. Now, if you can construct the universal cover, then the automorphism group of the fundamental cover is uh, simply connected. The fundamental cover is going to be the fundamental group, right? So I can't have a response, so I don't know where to stop. But unfortunately, simply connected covers cannot be constructed right away in the category of schemes. You have to naturally move on to pro schemes. I can keep talking about it,
No,
but the
fine.
basic idea
Yes,
was just to take a detour from there and just use finite covering spaces. The analogy was to use finite ethyl morphisms here and define the profinite completion of the fundamental group as just the fundamental.
Okay, so I can address the next question. If a category has finite limits, is it obvious that the algebra of home sets induced from the type of algebra each objects are? So basically, just having objects like to possess some algebraic structure is not sufficient. You also need the morphisms to respect or to preserve that kind of algebraic structure. So that will be a necessary condition for the algebra of home sets to reflect the algebra inside each object. Yeah, it's not direct. It's all interdependent. Yeah, it's we can't directly jump to conclusions. Category, you should always remember, it's about objects as well as morphisms. So if the morphisms do not respect those, like so for example, you start with the category whose objects are groups, and then the morphisms are simply functions. They don't care about groups. Then you are recovering the category of sets up to up to equivalence. So morphisms are really important here. I understand your question is still related to enriched categories.
Not sure about his question though. Is it obvious that
I
algebra
think
of form sets?
yeah, I think I got the gist. Am I correct, Pranay?
What is algebra of form sets?
Yes, I understood now.
Yeah, okay.
Okay.
Does anybody have any questions?
So
We'll
maybe we
wait
will
for.
wait for a minute, and if
Yeah,
there are any
exactly. We'll
queries,
wait for a minute and then otherwise we'll stop. Yeah.
definitely, sir.
Well, I should also add that since it's just two of you, if you have any questions after this, I'm not sure how many people will actually write the exam. I hope that Virat can write it. He has been submitting the assignments regularly. Yes, examination is on the 27th October and 16 students are registered. I understand, Murli, but many students have not got they haven't submitted assignments. So I'm not sure whether even if they write the exam, they can pass.
Okay, he's
Only a
asking for
couple of
tips.
Yes, sir.
students
They
have
need to
been.
meet a minimum criteria
Yes,
in
exactly,
the
exactly.
assignments.
In the assignments, and if they
Right.
haven't fulfilled that, I'm not sure they will write the exams.
But
So
irrespective of submitting the assignments, they can appear for the examination, sir.
they can. Yeah,
Yeah, they
okay.
can, sir.
So tips for exam preparation, fine. So you should just focus on the assignments, I would say. Yeah, you will understand the type of questions I can ask in the exam if you look at the assignments. Yeah, it shouldn't differ too much. The format won't differ a lot. There will be some open questions, obviously, and those, I mean, open as in unseen questions, but 50% of the paper has to be very similar to the assignment. So hopefully, if you are writing exam, it shouldn't be hard to pass. Yes,
Virat has
Virat
got
is
a
asking, yeah,
question. Where can
where
I
I can
study?
study about E infinity
Well,
rings.
move on to Lori's text on higher algebra. The first chapter, I guess. Maybe before or after operads, he discusses the infinity rings. That's the goal. Hmm.
And Virat, if you have more questions, like definitely I'm not the person to ask. Like you should contact Dipankar directly. I'm
Okay.
not an algebraic geometer by any means. I like
Neither am
category
I.
theory for its own sake.
I'm an
You
algebraic
are?
geometer, but a fake one. So category theorist at heart. So might not be very helpful for algebraic geometry. Peter Johnston.
Oh.
Deepankar, Virat is asking for your email ID. Can we give?
Sure.
Ask Virat to yeah, just send an email to the course website.
That
And
is
then we
on the
will
forum, no, sir,
yeah,
discussion forum.
yeah, on the
All right,
discussion
sir.
forum, and then he will answer your question.
Right, sir. Right, sir.
Bring Peter Johnston to IIT-K. I don't think
That's
now he's too old now. I'm not sure he will.
Is the third volume really published?
I I think I got a copy. The
Really?
third one, I got a copy.
Cohomology of two causes.
I'm not sure if that is the content, but yeah, a few years ago, I could get that.
Can you send me the copy?
Yeah, I will try to look for it. Yeah, if I have it on my old
Okay.
laptop, then I'll search for it. Well, I'm not
I
sure,
thought he has-
Pranay, I can do that. This bringing him into IIT Kanpur. But I think like recently he was present at some meet in Europe. If you get funding and you go to a category theory meeting where is in an invited speaker, you can go and talk to him. Recently he was in Spain, like a few months ago. That much I know.
Can we wait more?
So yeah, Virat, you can just drop an email and then Dipankar will share his personal email ID with you. Fine. Shall we call it a day?
Yes, we can close. Thank you so much
Yeah,
for
we
your
can
valuable
close.
time. Thank you, Dipankar. Pranay, we are going to close the session.
And thanks, Murli,
You're
for
welcome, sir.
conducting this. Yeah.
Thank you, sir.
I hope this remains forever in YouTube and helps people get
Yes,
started
yes.
with
Yeah.
their PhD
Yes.
work.
It will be available.
It will help people to not study category theory, but something else. Yeah.
Yeah. To get started with their PhD, they would need this for a couple of years and then they would forget.
Okay.
All right, sir. Thank you, sir. Thank you, Dipankar.
Okay. Bye.
Bye bye.
Yeah, bye.